In section 4 of chapter 3, we're going to be continuing with factoring. This is going to be a really useful skill because technically you don't need to know this stuff. However, it's going to make certain factoring problems so much easier if you do. All right. There are two specific factoring techniques that I want to go over. Seeing as how factoring is the inverse of multiplication, I want to go through the multiplication process first so that we can learn to recognize what they are and how they work. There are two specific cases. The first one is called perfect squares. If you have the quantity 2x plus 3 quantity squared as an example, if you were to multiply that out, realize that that is the same thing as 2x plus 3 times 2x plus 3. If you're squaring something, you're just multiplying it by itself. If you drew an area model to multiply those out, it would look like this. 2x plus 3 on top, 2x plus 3 on bottom. As a little note, as an aside, for any of you that were ever wondering why a second power we refer to as square, it's because if you drew an area model to represent it being multiplied out, then the length and the width would be the same measurement, meaning it would be a square. That's why these are called squares. 2x times 2x is 4x squared. 2x times 3 is going to be 6x. 2x and 3 is going to be another 6x. And then 3 and 3 give me 9. The answer is going to be 4x squared plus these two are like terms. 6x and 6x give me a 12x. Then the plus 9 at the end. This is the answer if we were just trying to multiply it out. However, our goal is to be able to recognize a certain characteristic. Our goal, since we're factoring, which is this backwards, is since this is a special case, it's something being squared, we want to find a way to just skip all this. And there is a way. If I gave you a problem like this to factor, there are a few indicators that will tell you if you can just jump from that problem straight to the factored solution without doing an area model. Here are the indicators. The first term is going to be a perfect square. That's just 2x if you squared it. The third term is also going to be a perfect square. It's just 3 if you squared it. The middle term is going to be 2x times 3 times 2. Now, why am I multiplying it by 2? Because there were 2 of them in the area model. If that pattern holds true, if you were left with a problem to factor where the first term is a perfect square, the second term is a perfect square, and the middle is the product of those two squares times 2, then you can go straight from the problem to the factored version, 2x plus 3 quantity squared. Now that said, of the two techniques I'm going to be going over right now, if you're only going to have the brain capacity to know one of them, this is the one to forget. Because the area model always works on this one. And it'll work really straightforward. There's no issue if you ever had to factor 4x squared plus 12x plus 9 and you use the area model. It will always work. There is no issue with it. The next one, however, will be confusing if you do not know this shortcut. That said, it is the easiest to identify and it is the easiest to do. This one is for a difference of squares. It'll make sense why it's called a difference of squares in a second. If you were to multiply these two binomials together, we'd get an area model. It would go 5x plus 8 and 5x minus 8. 5x times 5x is 25x. 5x times 8 is 40x. 5x and negative 8 give me negative 40x. And negative 8 and positive 8 give me negative 64. That would give me a 25, oops, I forgot the square there. 25x squared. These two terms are like terms, but they're opposites, so they cancel each other. And so you're just left with the minus 64. So that's what happens when you multiply it out. If I gave you this problem to factor, here are the patterns to recognize that it'll turn into something like this. Just like the perfect squares, the first term is going to be a perfect square. That's just 5x times 5x. The second term is also going to be a perfect square. And lastly, you need to separate it with a minus sign. That's why this technique is called a difference, or subtracting, of squares. These are both perfect squares. These are the easiest to identify because out of all the factoring problems I will give you, this is the only one that's a binomial. It only has two terms. Most of them are trinomials. Most of them have 3 parts to them. If your problem ever has exclusively 2 parts, you have to use a difference of squares. If you can't use difference of squares, it's not factorable. What that means is if this is a plus sign, can't be factored. If this is a perfect square but this isn't, can't be factored. These both need to be perfect squares and you have to have a minus sign. If either of those things don't happen, not factorable. You just stop. So here's a set of problems that these special attributes do apply to. On the first 2, I'm going to show you how I recognize them. On the last 2, I'm going to show you how quick you can do it. So problem number 1, I have 36x squared minus 60x plus 25. When I, as a mathematician, read that, I have alarm bells in my head going off because of 2 very, very particular things. First, this is a perfect square. That's just 6x times 6x, which is 6x squared. There's one bell going off. The other bell is that this is a perfect square. That's just 5 times 5. So first I recognize that the first term and the last term are perfect squares. If this is a perfect square when factored, then what that means is this middle term has to be this 6x times this 5 times 2. And 6x times 5 is 30x. 30x times 2 is, in fact, 60. We don't care about the negative right now. We just care that it's a 60. So since the last 2 terms, the first term and the last term, the end terms are perfect squares, and the middle does match that pattern, I can immediately just jump straight to my answer. 6x and 5, and then whatever symbol's right here, that's the symbol that goes in between them. Done. I didn't have to do an area model. For problem number 2, again, this one, it screams at me because it is a binomial. There's only 2 terms. There's a 49x squared minus 1. The only way a binomial is factorable is if the first term is a perfect square. That's just 7x times 7x. The last term has to be a perfect square. I don't know why. This throws students off. 1 is a perfect square. It's just 1 times 1. And it has to be a minus sign between them. All 3 of those things check out for this problem, so I can just jump straight to the problem, the answer. 7x plus 1 times 7x minus 1. Done. So right now I showed in black what was going on in my head. Now I'm going to show you what actually goes on verbally and how fast I can do these while still explaining. Problem number 3, I have 144 minus 9x squared. I know 144 is just 12 times 12. I know 9x squared is just 9x times 9x. This middle term is a minus sign. So here's my answer. 12 plus 3x times 12 minus 3x. Notice I went straight to my answer. I didn't have to skip anything. I didn't have to write anything. I just went straight to the answer. Again, that's why this is really hard for me as a grader to grade, because I have no work to go off of. If you miss a negative, I got to mark you down for that. This is the one and only skill throughout the entire year where I get to do that. And I don't like it, but there's nothing I can do. I can't assume that you know it. All right, number 4. This is a perfect square. This is just 4 times 4. This is a perfect square. This is just x times x. This will turn into a perfect square when factored if it's 4 times x times 2. That's 8x. That's in the middle. So it's going to give me 4 plus x, quantity squared. Or that's the same thing as x plus 4, quantity squared. Now the one question I was asked, and I want to make sure I've referenced this, even though I don't have an example. If there's a negative in front, can you still factor? Yes, but you can factor by rearranging things. What I mean is, the green problem, I could have rewritten it as the following. It's the same thing. We typically like having the negative term second, but you can technically have it first. And it would still factor to give you the same answer. So recognize you can swap terms around as long as they maintain the positivity they already have. Because 5 plus 2 is the same thing as 2 plus 5. 7 minus 8 is the same thing as negative 8 plus 7. But as long as you follow those patterns, you should do great.